Okay, good morning, everybody. Thank you for joining. So as Gio mentioned, I'll give you some initial overview of some of the results from our V2 water cycle simulation campaign. And today will be just an overview of some of the couple simulations at low resolution. So this is a work from a very large group of people. I have not listed all of them here. I listed only myself and Luke, but everybody will be included in the upcoming overview paper. And many of the figures that I'll show today are part of the draft that we are working on describing the model. So in a very high-level summary, what is new and different in V2 compared to V1? Essentially, it's faster and better, at least mostly better. In terms of faster, you've heard me say that before, it's approximately 2 times faster on identical machines, with throughputs up to 40 simulated year per day. The improvements that we have are related to improved clouds and precipitation, including cloud feedback, leading to a much more realistic or plausible climate sensitivity of 4 Kelvin instead of 5.3 earlier. And instead of having a single configuration, we have 2 configurations. One is a low-res configuration with 100 kilometer atmosphere and land, half-degree river, and 60 to 30 kilometer ocean and sea ice. And we also have something new for V2, which is a regional refined configuration that is fully coupled. We had a regional refined configuration before, but they were not fully coupled. So that will be 25 kilometer in the atmosphere, 1/8 degree river, and 14 down to 14 kilometer for the sea ice and ocean over North America. This is where we are in terms of the simulation campaign. I don't need to go through all of them, but we are basically doing with the low-res, we're doing the direct plus historical simulation. We have been doing some DAMIP-like simulation, which are essentially single forcing couple simulation. We have done some RF-mid simulation to compute effective radiative forcing. And then we're going to do a large subset of those simulations as well with the regional refined model. And she has done the PI control and 1 historical simulation, and we'll do more simulation shortly. So we have more than 6,000 simulation at low res to date, and over 1,600 using the North American regional refined configuration. So as I mentioned, the model is substantially faster. This is a performance comparison for the couple model. This is performance on our chrysalis cluster. Blue is V1, red is V2. This is the overall performance of the couple system. And you see that if you scale up to the limit, we now have throughput of 40 plus simulated year per day compared to 20 something with V1. This is running on identical machine. And if you look at the breakthrough, the throughput versus the cores that the model is using, the area basically tells you how expensive a component is. So you can see that the atmosphere here became substantially cheaper between V1 and V2. So did the ocean. And the coupler stayed about the same. The sea ice became a little bit more expensive in V2, mostly due to the addition of more snow layers on sea ice. We are kind of in an odd situation here where the sea ice now is almost as expensive as the ocean. So I think there's room for improvement in the performance of the sea ice for future version. Now zooming in on the atmosphere, maybe let's just focus on the plot on the right, which shows the atmosphere cost broken down in various components. In red is the tracer transport, purple, the rest of the dynamic core, so the basic equations, then the rest of the atmosphere, which is mostly the physics. So you see a dramatic change between V1 and V2. A large portion of it comes from the tracer transport, which almost went down by probably 80% or so. This is really wonderful news for future applications that rely on additional tracers like aerosol and chemistry. And the rest of the dichrome actually went down as well. This is a substantial achievement because we also have the ability to do non-hydrostatic with that dichrome now. And then the rest of the atmosphere went down by also nearly a factor 2 due to the use of the physics grid, which you've heard before. In terms of climatology, this is the precipitation from the historical ensemble of the simulation. This is averaging over 30 years, 1985, 2014. But this is after the 1,000-year spin-up, several hundred years of PI control, and the historical simulation. So there is over 1,000 years that precede those figures. So there is a lot of time for the model to drift and go into a crazy regime. So this is really a good test of how stable the climate is in the couple system. And you can see this is the precipitation bias in V1 compared to V2. Overall, we have a 15% reduction in root mean square error, going from 1.13 to 0.97. That may not sound like a lot, but this is for anybody who has actually tried to tune the couple model. They will know that this is a lot of effort. Reducing our MSE precip is very difficult. So this is significant at 15%. I would challenge the V3 development to try to do something comparable in V3 compared to V2. And if we achieve that, we could go down to 0.8 range or so. That would put us among the best model out there. So we've come a long way, but we can still get better. Some of the improvement came from regional improvement. You can see a significant reduction in the double ITCZ. It's still present, but it's much weaker than it was. The Amazon dry bias here is also much improved compared to V1. And we also have improvement in the excessive precipitation over the tropical warm pool, Western North America, and as well as over high elevation. It's a more modest improvement, but there is some improvement there. The clouds have also gotten better. Although the picture look quite similar, if you look regionally, you see differences. For example, one notable one is in the shortwave cloud radiative effect, the improvement over the key stratocumulus regions. We still have a bias, a deficit of clouds, but you can see that the red is much smaller and not as deep as it was in V1. So there's significant improvement in those three regions in V2 compared to V1, as well as a global improvement, a reduction in the RMSE, and a reduction in the mean bias. For shortwave and long wave stays more or less the same. Some regional changes. But we didn't just focus on improving the clouds from a radiation point of view. We also focused on trying to improve them at the process level. And here's an example of some of those improvements. In V1, we had a rather unrealistic behavior when you look at the liquid cloud fraction as a function of temperature. This is over the southern latitude band, 30 to 80 degrees. We had that rather unrealistic feature of a shoulder here, where over a fairly wide range of temperature, the liquid cloud fraction stayed the same. And that really is not something that is seen in the observation here in black. That has been corrected thanks to lots of efforts by Shui, Polun, and many others to retune the clouds. And in V2, it's much more realistic. We got rid of that unrealistic behavior, and we also got much closer to the observation here. I should mention the observation have a large uncertainty, so we should not expect to necessarily exactly match the black line here. But clearly, the blue line is much better than it was in V1. Some plots about tropical variability, the Wheeler-Kiladis. We're doing reasonably well in terms of MJO, but we miss a little bit of amplitude as well as equatorial Rossby waves. Here, the amplitude is a little bit underestimated, but we dramatically underestimate the variability with Kelvin waves in this region compared to observation. So we have very little Kelvin waves compared to observation. So this is something maybe to pay attention in future version this is often related to parameterized deep convection, and sometimes this is a symptom of overactive deep convective parameterization that just kills resolved waves. MJO, V1 did pretty good at MJO, and V2 continues to do so. Jim Benedict is very optimistic, so he thinks V2 is actually slightly better than V1 in the sense that the propagation extends a little bit further east. So this is the observation, and this is the propagation highlighted in green. You can see that we do propagate a little further, but east of 120 or so, the propagation speed doesn't match the observation very well. Ozone and ozone hole, we have an ozone hole. This is the time series from 1850 to 2015. Minimum total ozone area. So you see that we do have the model is in blue, the observation in black. We have an ozone hole at about the right time with about the right shape, but the minimum is too high compared to observation. Climatologically, so looking at that period seasonally, we also captured the seasonal variation of the ozone hole quite well. But again, we are underestimating the amplitude of the seasonal change. Now moving on to some high-level measure of the model. So first looking at equilibrium climate sensitivity and the transient climate response. You get this from running 1% CO2 simulation and about 4 times CO2 simulation. So the estimate, the ECS, this was V1, this is V2. We went from 5.3 to 4. That's a very significant reduction, and now we are within plausible range. There was a large effort by Sherwood et al. To review the literature and come up with a best estimate of ECS, and their best estimate range is 2.6 to 3.9 or 2.3 to 4.7, depending on assumptions. So with an ECF of 4, we are basically within their line, within their estimate. That reduction in ECS came from a change in the slope, as you can see here. That's mostly related to change in the cloud feedback, but also a reduction in the effective 2 times CO2 forcing. For the 1% CO2 and the TCR, that's the simulation shown in blue here. The model doesn't warm as much, and the TCR went down from 2.93 to 2.41. So on this front, the news is good. We went from something clearly unreasonable to something that is now high, but within the range of possibilities. Now moving on to the effective radiative forcing, we did RME simulation to compute both the total forcing and the aerosol-related forcing, comparing V2 and V1. For the aerosol forcing, the magnitude went down a little bit from minus 1.65 to minus 1.53. We tried to get that even lower, but at the end we couldn't. There were some late changes that came in that actually made it larger again. So, but we still ended up a little bit smaller than it was in V1. The total forcing, which we didn't estimate until after the model was frozen, also went down actually. So you would expect that if this magnitude is reduced, that the total forcing would go up. That's not the case here. And I think that's related to the CO2 effective forcing going down as well. Similarly to the Sherwood effort, there has been an effort by Bedouin et al. To try to come with an estimated range for the total aerosol forcing, and their range with 68% uncertainty is minus 1.6 to minus 0.6. So we are right at the edge here, but we are within the range that study came up with. So again, from that point of view, it looks like everything is good. But then we did the historical simulation, and unfortunately, that doesn't look quite as good. So this is the temperature, global mean surface air temperature anomalies from 1850 to 2015. The gray line is one of the observation product, Hadley CRUT5 analysis. And then the red is E3S and V1 with the shading representing the ensemble range, and then V2 in blue, again, with the shading of the 5 ensemble members. And V2 is quite similar to V1, but actually slightly worse in the sense that starting in the 1940 or so, it is a little bit colder than V1, and it essentially remains colder than V1 for most of the period thereafter. So we still have the problem of excessive cooling here in the 60s and future, and then we start to catch up with, but we don't quite catch up in V1 by the end of the historical record. So that's a bit of disappointment for V2. But Dave tried to convince me very hard that this was a great finding nevertheless. So what we did is to understand this, Dave had a great idea of doing some single forcing simulation. So those are fully coupled simulation where you turn on and off selected forcing. So we decompose the total forcing in 3. One is the greenhouse gas. And this is for V2 is shown in red here. So when you have only greenhouse gases, the model just warms exponentially, as you would expect. One is when you have only the aerosol. So in V2 is the light blue line here. And you can see that the model cools due to the aerosol effect and eventually plateaus here because of pollution control that came into effect in North America and Europe. The rest of the terms, which include solar variability, land use, land cover, ozone, gives you the green line, which and volcanoes as well. The green line has oscillation, but it's mostly flat. So the big terms are the greenhouse gas, which warms, and the aerosol, which cool. And you can see that they look very similar to each other in magnitude, at least up to the late 20th century, which is why for a large part of the historical record, we see no warming. It's because the greenhouse gas warming is masked by the very strong aerosol forcing here. If you sum all the terms together, you get that thin blue lines here, which is compared to the actual E3S and V2 in the thicker blue line here. And you can see that the sum of the term reproduces nicely the original ensemble. So the system is quite linear. The decomposition is linear in that sense, and we can reproduce it by decomposing term on term. So based on that, now we can play around with those single forcing simulation a little bit, and we treat them as linear perturbation from PI control. And as I showed you on the global mean surface temperature plot, the linear assumption is a good one. So you can, for any variable, that could be a time series or climatology, you can basically write it as the PI control plus a perturbation from the greenhouse gas. So you take the difference between greenhouse gas and PI control, the perturbation that comes from the aerosol, and then the perturbation from all the other terms. So if you just sum all this, you recover the whole forcing, but you could also add a factor here, alpha greenhouse gas and alpha aerosol, to get hypothetical configuration where the greenhouse gas effect might be weaker or stronger, or the aerosol effect might be weaker and stronger. And this is inspired by similar work by Nealon et al. 2010, but they did that for perturbing parameters rather than using single forcing simulation. So with these two parameters, alpha greenhouse gas, we can essentially modulate the response of the model to greenhouse gas, which is sort of a proxy for modulating TCR and ECS. You have to be careful because the time horizon might be different. So I don't want to say it's exactly the same. And then by changing alpha EAR, we can change the strength of the model aerosol forcing. And then we can reconstruct any field that we are interested in. So I did that, and I constructed a cost function that measured the mismatch of the hemispheric mean surface air temperature on an annual basis. I did separately for Northern Hemisphere and Southern Hemisphere because the aerosol signal has a very strong asymmetry. And the cost function spans the period from 1950 to 2015. And then this is very cheap, so you can actually evaluate the cost function through the entire space. So on the x-axis is modulating the greenhouse gas response. On the y-axis is modulating the aerosol response. So the one point here is E3SMV2. And you can see that the cost function has quite interesting shape. We have a relatively broad valley here, but the global minimum is here. So let's start with E3SMV2 here. And if we wanted to improve V2, let's consider a few different options. One is assuming that the aerosol response is correct. What would it take to try to get a better 20th century? Well, we would have to move down the slope this way, essentially increasing the greenhouse gas response, so essentially increasing TCR or possibly ECS. So this is trying to balance a strong aerosol forcing with a high sensitivity model. This is somewhat what we did in V1. And I think that also explains why there was a slight degradation from V1 to V2. I think V1 was closer to here in the space. So even though we improve ECS going from V1 to V2, we actually ended up moving uphill in that space of the 20th century. So that's one way we could try to improve the 20th century. Another way, assuming that the greenhouse gas response is reasonable, what would it take in terms of changing the aerosol response? So in that case, you would quite dramatically have to reduce the response by about 60% to get closer there. And that minimum is actually much closer to the global minimum. And if you did both, you would get somewhere here. That would be about a 25% reduction in the response to greenhouse gas. So again, if you translate that to ECS, we'll be maybe going from ECS of 4 to 3. But I caution that it doesn't have to work that way because the time horizon is different. And then on the aerosol side, we would be looking at an 80% reduction in the aerosol. So this is what it looks like when you actually reconstruct the global mean surface air temperature for those composite configuration. So again, in blue is V2. And the best solution, the global minimum, is shown in yellow here. And you can see that it matches quite well the historical record. And this is the case for both global, but also northern and southern hemisphere separately. I don't have the plots, but they both match. The solution where we try to hold the aerosol constant and balance it with a stronger response from greenhouse gas is shown here in orange. And you see that kind of pattern of lack of warming here and then excessive warming later. Clearly, that's not a very good match, especially if you imagine extending that another 10 years. This may be really way off the observation given the trend in the last decade or so. So that doesn't look like a very reasonable path forward. The path of holding the greenhouse gas response constant and changing the aerosol is the purple line here, and it's actually quite close to the best solution. It departs a little bit later on and maybe a stronger response in the warming in the 21st century. So the two most promising approach is the best and the holding. This one was a reduction in both 25 reduction in greenhouse gas effect, 60 and 80% reduction in aerosol forcing, and this one is about 60% reduction in aerosol forcing. But in addition to looking at the global mean surface temperature, you can actually recompose what climatological field might look like, because you can also recompose them using that linear decomposition. And this is what you get for the top of the atmosphere net shortwave. This is the model. So this is net shortwave TOA between 1985 2014 in the E3SMV2 historical ensemble. And this is that composite simulation where we have scaled the greenhouse gas and the aerosol to match the best point that we found in that cost function. And if you look at the difference of the two, it's not dramatic, but if you look more closely, it's actually pretty significant. And I'm still amazed by that figure because you really see the blue area here, especially over the northern latitudes, ocean, Pacific, and Atlantic, you see that go away. And this is really the first time I've seen, this is what happens when you remove the excessive aerosol forcing. Even when it's only based on the global mean surface temperature, and the shortwave gets substantially better. So you remove those large hemispheric biases, the root mean square error gets much better, and look at the mean bias, basically zero compared to what we had before. And you see the difference here. Most of the impact is in the northern hemisphere. You can do the same with sea surface temperature. And you see between those two here, we will get a pretty substantial improvement again in the northern Pacific and northern Atlantic. We certainly would not get rid of all of SST biases, but clearly some of the excessive cold bias in the Pacific and the Atlantic is related to the excessively strong aerosol forcing. Now, the southern hemisphere is a different story altogether. So in summary, I hope I've made the case that V2 improves upon V1 in many aspects. It is substantially faster, which is a testament to all the work that went into improving the algorithms in V2. And we have improved clouds, precipitation, and other aspects of the simulations. And in addition, we have a much more realistic cloud feedback and equilibrium climate sensitivity. Now we can claim that we are within the range of what's plausible, which was not the case in V1. Nevertheless, we continue to have challenges, and the main one that I showed today is that V1 fails to accurately simulate the late historical temperature record. This is despite having ECS and aerosol forcing that are within the range of what's considered to be plausible. Despite that, we failed to simulate the 20th century. And I think that shows that those estimates are simply not enough to constrain the 20th century. And in this analysis, in order to correct the 20th century, we're looking at a very significant reduction in aerosol cloud impacts, somewhere between 60 to 80%. So this is really, I was quite taken aback by the amount of by which we would have to reduce aerosol cloud impact to correct the 20th century problem. This is very substantial, and maybe it just tells us that aerosol cloud interaction is just not as important as we used to think. So there's a lot more to come. Luke and we'll have more results on ocean and sea ice in a future talk. And as I mentioned, we are running a simulation campaign on North American RM configuration, and there will be results when that is ready. Thank you for your time.